Okay, I guess we can start again. Welcome to the last session of this series. So this is just a reminder what we discussed yesterday. Yeah, so the fact that in a general space-time, there's this principal problem or complication that you can have in Hamiltonian that is not constant in time. Yeah, so that means there is no time-like killing vector in general, which in turn means that you can't really sort of distinguish positive and negative frequency modes. Yeah, but on the other hand, distinguishing positive and negative frequencies is absolutely essential to define what we mean by a particle. Yeah, so this is illustrated here, like if you just take a simple scalar field, this is the Klein-Gordon equation for an arbitrary metric, then you can find some set of complete solutions to this equation, yeah, and expand the field. You promote it to an operator by introducing the standard annihilation and creation operators. But since this is not unique, I mean, the distinction between positive and negative frequencies, so the distinction between the time coordinate is not singled out, since there is time dependence in general, you can find a different set of modes, yeah, but that is also complete and orthonormal. Yeah, but since both are complete and orthonormal sets, you can express one in terms of the others, in terms of just a linear combination. Yeah, and the point here is that this general linear combination will mix positive and negative frequency modes. Yeah, so in Minkowski space, yeah, when time is conserved, or in any space-time when time is conserved, you would not mix positive and negative frequency modes in this way. Yeah, you can, of course, always define a new set of modes, I mean, new sets of modes in terms of the old ones, but you don't mix positive and negative frequencies. But if you do, so this condition here is just rewritten using the orthonormality of these mode solutions, V and K. Yeah, that also means that the creation and annihilation operators mix, meaning that if you define your vacuum state with respect to one set of modes, it's no longer a vacuum state with respect to the other modes. Yeah, so that's a crucial general thing in curved spacetime. So super confusing if you see it the first time, and the more often you see it, the more you get sort of used to it, but it's still a bit annoying. Yeah. Okay, good. So what we want to do today is to basically look at a toy example and see how this works in practice. Yeah. Yeah, so this largely follows a discussion that was published last year. Yeah, and by the way, I should mention that I maybe put out the lecture notes. Yeah, so they are about to be put out, so they are in the process of being published on the webpage. And I mean, it's very rare that I give actual explicit references to the literature. But just let me know, like if you wonder about concrete references to read up or to find statements in the literature and so on, just let me know and I'm more than happy to provide more details. Okay, so the toy example that I want to discuss here is the case, well, obviously we always have gravity, you know, we can't switch off gravity, but then let's consider that we just have two scalar fields. One that should be our dark matter field. So this, let's say that there are no interactions with the standard model, no interactions with the other scalar fields, so really just a free scalar field. So a kinetic term and even an extremely simple potential, so just a mass term. Yeah, so then from the point of view of ordinary quantum field theory, we would say that, okay, we can't do anything with this. Yeah, we can derive a propagator, but it will not interact with anything, nothing. Okay, and then this one here, this is basically the inflaton. Yeah, I told you that this kind of particle production is most relevant during reheating, yeah, so at the end of inflation. So this is supposed to drive inflation. So here we have, again, just a scalar field. And then we have a potential that is such that we get inflation. So this is the field that is responsible for inflation, meaning that here we want to consider a field that is always subdominant. So we start with zero initial abundance, and we keep it subdominant. While inflaton field. While this inflaton field is really the one that dominates the matter density. Okay, so just to put things into context, that means that let me take a new breakboard. So we want to consider a situation where for the inflaton field, we have some kind of potential, and then you know that, we will start at some point here in the potential and then have ordinary slow roll inflation until we get close to the minimum of the potential. And then there are, during reheating, basically fast oscillations at the bottom of the potential. So if we plot this in terms of time, the energy constant of the inflaton, so then we would have a potential energy at some point. So this is still during inflation. And then you have these fast oscillations. So this is the potential energy. And on the other hand, as we leave the slow roll regime, the kinetic energy, so this is rho kin, will start to build, and then basically in this, at the bottom of this potential, at the minimum, oscillate. So that means that the total one is an envelope, but it's still, you can still see these fast oscillations. And these are very fast oscillations, and the reason I'm stressing that is that for the particle production that we want to discuss, it's really crucial that you have fast oscillations. So typically, if you have a slowly changing space-time, you won't produce any particles in any appreciable way. Okay, so this is just to understand the basic setup, and now we want to understand, at least in sort of the starting steps, how to calculate particle production in practice. Okay, so first thing is that it's often a very good idea when you have these kind of potentials, and of course we want to look at the Friedmann-Robertson-Walker metric, to change coordinates to conformal time. So we introduce the conformal time like this. That means that our metric is just given by the scale factor times the Minkowski metric. And of course then it's a function of the conformal time. And that's why it's called conformal time, because it's just an overall factor. But here it's not a conformal transformation, but actually a coordinate transformation. Okay, so then we can also redefine our scalar field chi. So we basically factor out one factor of the scale factor. And then our Lagrangian reads as follows. So then we have a 1/2 chi prime squared. So the prime denotes derivative with respect to conformal time. And then the remaining terms can be written in this form, where omega squared is minus the Laplacian plus a squared mass squared minus a, and the second time derivative divided by a. So this one here in Fourier space will just be a k squared. And here that's something that you can see here. We are looking at a decelerated expansion. So our, I mean, this term here will always be positive. Yeah, and in position space, it's a differential operator, but in Fourier space, it's just a real number. Okay, and you can also see that, I mean, there is a scale factor that is entering here. Yeah, so from this term, from this expression, you see that, well, the omega, the frequency, is time dependent. Yeah, and that means in this language here directly that in this kind of setup we will have particle production. Okay, so then let's do this kind of mode expansion in the same way as here. So we introduce a chi, I mean, this is our chi twiddle. We write this as a mode expansion. So we turn to Fourier space. And we write then these modes here, yeah, so they are only time dependent or eta dependent, as fk ak plus fk star a k dagger. So that, I mean, if you compare it with what I've written here, then these f's, these are basically the modes. Yeah, so they correspond to like the modes UK. Okay, but then we can also look at the conjugate momentum. Yeah, so we know that pi is just so the conjugate momentum is the derivative of the Lagrangian with respect to the time derivative of the field. Yeah, so then we can also expand this in terms of mode expansions. So we have a pi twiddle beta. Yeah, and then we can write this, these momentum modes also in terms of annihilation and creation operators, yeah, because we know it must be an operator, and we know that, I mean, the way we set this up is that these operators describe the entire Hilbert space. So we can write this. So this was a k here, and then we have a k here, and then I can introduce modes G. Yeah, so this is just, I mean, a way of parameterizing the momentum operator. So while I said that these f's correspond to the u's, yeah, don't think of the g's as corresponding to v's. Yeah, it's rather that we just use an arbitrary parameterization here. Okay, so now let's make an ansatz to solve these. So for the fk, we write like this. And of course, the reason I call this alpha and beta is motivated here, but I also put a twiddle in order to make sure that you don't confuse it with the alphas and betas there. So they're not exactly the same. They're related to the alphas and betas there, and we will see how. Yeah, so this is really just a formal ansatz. So this is just some function. So I basically just divide out the, I mean, I just extract a normalization factor here for convenience. And then I do something similar for the momentum modes. Okay, so why do I make this ansatz? Yeah, of course, I can just make it as an ansatz. I mean, I exchange basically two so far undetermined functions with two new undetermined functions, alpha twiddle and beta twiddle. Yeah, so mathematically, I can just do whatever I like then. But the point is that with this ansatz, I get a direct interpretation of these modes alpha twiddle and beta twiddle because I can recognize the structure that I have in flat spacetime. Yeah, so in particular, so in flat spacetime, I get the correct normalization with these factors. So flat space-time. Normalization. And how do I see this? Well, I have to choose my alpha twiddle to just be the like the phase factor, the phase that you get from the time dependence, and beta to be 0. So then that is the typical positive frequency mode. The F would be just the positive frequency mode that you have in the space-time solution, just an ordinary plane wave. And in fact, you need this here in order to make the modes normalized. Yeah, so I said here that in this description, we need normalized, orthonormalized modes, and that requires this normalization factor. Yeah, and that's typically also what you have seen, and even if you just study quantum field theory in flat space, yeah, the typical way you expand your quantum fields is exactly in terms of, I mean, this expansion here with this normalization, and then for the momentum operator, you get these normalizations for consistency, and that's what you need in order to find, I mean, your typical like commutation relations between the conjugate momentum and phi, yeah, when you translate that to the commutation relation between A and A dagger. Yeah, so this is the canonical quantization quantum mechanics or field theory then, and the fact that these are just orthonormalized comes from this normalization here. Yeah? Okay, so that's why this is a useful ansatz. But of course we still have to solve it. Yeah, and then we can solve this because we have two conditions. And of course I forgot. Yes, so what I should maybe add here. So this is the Lagrangian. And then we get the Hamiltonian from this, as usual, by a Legendre transformation. So this is a one half pi squared plus 1/2 chi squared omega squared chi. Yeah, and my previous remark about the fact that because omega is time dependent, the Hamiltonian is time dependent, you can see here explicitly. Yeah, so basically what we want to do now is to determine these two functions by using the Hamiltonian equations of motion. Yeah, so, and that is one that, well, we have this, we have the standard, yeah, so if we write this, so we just find chi prime, the time derivative with respect to the field. Yeah, so this is one condition. We know that if we take the time derivative of this equation, we should get this equation. So pk twiddle is equal to chi twiddle prime. And the other one is the equation, the Hamiltonian equation of motion. So if I take the time derivative of pi, this should be minus the derivative of the Lagrangian with respect to the field. So the Hamiltonian, sorry. So that we can just read off, so that's just the frequency squared. So then this is basically a coupled system of first order differential equations that we can use to solve for alpha twiddle and beta twiddle. So that's the idea. So we can rewrite this in terms of this actual system. Just to make this more explicit, what I just said. So this is basically our starting point. So we've just reformulated the system, but in the end it boils down to solving this differential set of equations. I won't do that, because that's actually involved. I just want to discuss the solutions here. I mean, you can actually see the or recover the flat space solution directly again, and that's a big advantage of using this parameterization. So that one we see. So in particular, as we said before, we want to start with initial conditions where the alpha k at some initial time, let's call it 0, can always shift it, is 1, and beta is 0. So then, if we do that, the first thing that we can discuss, the classical limit, if you wish, the flat space-time limit. If there's no time dependence, it means that the time derivative of omega is very small, or even vanishes. So what does that mean? Well, if we start with a 0 beta, and the time derivative vanishes, then beta stays 0. And also this term is 0, so we just have to solve this one here. So that means that alpha twiddle is, I mean, the solution of this is just an e to the I omega eta. And our beta k is 0. So that's exactly what we want to have. So we cover the flat space-time expectation. And now you can also see from this solution how this formulation relates to our general prescription. So basically, our alphas, alpha twiddles and beta twiddles, are related to these alphas and betas in the general formulation by just this phase factor that you would get in the standard approach. So with the normalization that we've introduced, this is basically a 2 omega k. So we're basically projecting out here this the ordinary evolution, the ordinary time dependence, and that's how alpha and beta are related. So, but that also means that this interpretation here will remain the same, because if I take the absolute value squared of the beta twiddle or the beta, that's the same. I just project out a phase. And I can directly see that in general, if I solve this set of equations, my beta will be time dependent. So that means I have particle production. So in other words, getting back to this general formulation, we start basically with modes at early times, eta equal to 0, where we've only a positive frequency mode. So my U is just the ordinary plane wave solution with the correct normalization. And then at later times, this entire solution, so this one here that I wrote there or there, that's what you should think of as this generalized solution. So we evolve from ordinary plane waves to a more complicated solution that is the full solution of the Klein-Gordon equation. Okay, so then we can do this, or the authors did this. So you can solve this differential equation by noting that we always stay in what you can call a freeze-and-like regime. So the occupation number still stays small all the time. So that, of course, allows you to simplify these equations, because here we can neglect this term, and here we can neglect this term. So that means that you can immediately write down a formal solution of this equation by just plugging this one here into that one and then integrating. Minus 2i. So you see that if you use this one here, you take the time derivative, then you get exactly the correct expression for the derivative of alpha. But, I mean, okay, so this is a formal solution. And the nice thing is that here, okay, so at this point, without these simplifications, this is a fully complete analytic expression. No assumptions have been made. Now we make the additional assumption that we always stay subdominant in the energy budget. So also a very innocent assumption. But then this expression here is actually quite complicated to evaluate, because you have these extremely fast oscillations, and remember the omega depends on time through the Hubble expansion. So you basically have to use in the expression for omega. Do I still have it here? No. The expression for the Hubble rate that you get from solving the background evolution equations for phi, for the dominant inflaton field. And then you, I mean, you need to do, like in practice, a WKB-like ansatz. You need to evaluate integrals with very fast oscillations. So the keyword is then stationary phase approximation and these kind of things. So it's actually a decent analytical calculation. But the nice thing is that you actually find a full result, so you can fully solve this analytically. And the result is as follows. So there are different regimes. So the first one is this regime. So that means we look at high momentum modes, high energies. By large, I mean larger than the energy scale set by the inflaton at reheating. So you can call that a high energy mode in the sense that we are looking at high energies larger than the inflaton mass. But you can also see, like from the comparison to the Hubble rate at the end of inflation, this is basically saying that we're looking at sub-horizon modes. Then the solution to this equation, I mean, again, it's fully analytic. I just don't want to write down all the prefactors. Is scaling with the momentum like minus 9.5. Yeah. Okay, so then you can also take the opposite limit. Yeah, that's harder to do. So in the end, I mean, you can do some approximations if you really go to the highly infrared limit. Yeah, otherwise you have to solve this numerically. So then you find a scaling that varies between -6 in the massless limit, so in the highly infrared part, and k to the -3 for large masses. Yeah, of course, I mean, the momentum cannot be smaller than the mass, so this is a condition on the mass of the dark matter particle of chi. Yeah, so for m chi approaching the inflaton mass, something like that. Okay. So this is just an explicit example. Yeah, I told you that, okay, this step here, this is a lot of work. Yeah, but it's this. This is a lot of work, but in principle straightforward. Yeah, that's just math. Yeah, so but the answer should be clear. So conceptually, it's very straightforward to use this formalism here and to actually calculate the production rate. Yeah, so this is really the occupation number of these particles chi. Yeah, but of course, it's still a bit, I mean, there seems to be a lot of formalism involved. So you can ask, okay, what is actually going on? Yeah, so, and in order to answer that, you can take a completely different approach and insist that you describe the entire process as sort of a perturbative process. Yeah, so you try to basically expand your metric. Yeah. And then, well, we can do it like this to keep things dimensionless. And by this way, introduce a graviton H. Yeah, so that means that our action in this perturbative expansion takes the following form. Yeah, we get some kinetic terms for the graviton. That's the standard like linearized gravity kinetic terms. Then we have the Lagrangian for the inflaton and the Lagrangian for the matter field. Yeah, and these are now, because we're doing this expansion, essentially given at the background level. And then, of course, we also have interactions between the graviton and the matter part. Yeah, so and the graviton couples, well, I mean, the only way it can couple is, of course, to the stress energy tensor. So we get a minus 1 over m Planck. Yeah, so graviton interactions are Planck scale suppressed. And the coupling to the, well, both the inflaton and the dark matter particle. Yeah, and in that kind of formulation, you can say that, oh, I mean, I don't need all of this. I can just directly read off interaction terms. Yeah, so this is an interaction Lagrangian. Yeah, this is a standard quantum field theory Lagrangian. So I can derive a propagator for my graviton. I know like the propagators for the fields. And this will give me an interaction term, because it will give an interaction between gravitons and inflatons, and it will give an interaction between gravitons and dark matter fields. Yeah, so what is really happening, you would argue, is that what we're looking at is something like this. Yeah, so we have inflatons in the initial state, and they annihilate via a graviton exchange to dark matter particles. Yeah? So this is sort of a much more intuitive physical picture of what is going on here. This is on flat spacetime because we do this expansion. Exactly. Yeah? So these are fields that live on flat spacetime. Yeah, but you would argue that, like physically, this is how I should understand this. I mean, this is only very locally. Yeah, in principle, you can do the same expansion around Friedmann-Robertson-Walker spacetime here. Yeah, but then you get like the background time evolution. So this is just the local argument. So locally in flat spacetime, so really in short moments of time, we have a constant production of particles in this way. And that's exactly what you should do for the Boltzmann approach, right? So basically, like for this production, we can use Boltzmann. So in other words, we use the Liouville operator for the expanding background and the collision operator in Minkowski space. And that's the motivation for why we do this expansion in Minkowski space, in order to derive the interactions, yeah, just for the purpose of calculating the collision operator. So in other words, this is what should really happen. Yeah, so I should stress that, I mean, this is a completely different perspective here. Yeah, and to start with, it's not at all clear that, I mean, you should get the same result. Yeah, because you really, like here you think of the background space-time as something dynamic, you refer to the question of how to define particles and so on. Well, this is a like very well-defined that matches the discussion that we had in the first part of the lectures. So in that sense, you should expect a commercial break now before I tell you the result. And you find that the phase space distribution for the dark matter particles, this is a function of the momenta k. This scales as this one. Yeah. And it does not only scale like this, but even the prefactor is analytically identical to this one. Yeah. So that's a very nice result. Yeah, so this is really identical to beta k squared. -1, yes, thanks. Yeah, that would be a bit disturbing. Would violate unitarity and everything. Exactly. Yeah, so we get only this one. So why don't we get this one? Yeah, and the reason is, well, this condition here. Yeah, in a perturbative approach, you annihilate two inflatons, and you always have a 3-point vertex of this type. Yeah, you annihilate two inflatons, two dark matter particles. So of course, you cannot produce dark matter particles with momentum smaller than the inflaton mass. Yeah? So that's why you cannot expect to recover this. Yeah? So in order to get, these are really non-perturbative results in this language here. Yeah? So it tells you that A, yes, there is an equivalence as expected, but it tells you also more about how the equivalence looks like, and it tells you that this is a much more complete and fundamental approach, though in practice it's considerably more difficult to calculate. Yeah? So what I showed you here, this is the kind of calculation that we could have done in the exercises. What is happening here takes more time than the exercise session. Yeah? I mean, it's also doable. It's not like magic, but it's much more involved at the technical level. Yeah. Sure. Yes. Very good. I don't know. Yeah. I mean, like, since as you say, I mean, it's a super horizon mode, Yeah, so you always then have to think about like coordinate artifacts, like what is actually gauge dependent and so on. So the fact that we have this kind of scaling doesn't mean at all that the physical energy density scales like this. Yeah, physical energy density is not even something that is defined. Yeah, so on super horizon modes, like before I was arguing with rho phi, rho chi and these things. So these only have a well-defined meaning inside the horizon. So outside the horizon, you need to try harder, define like gauge invariant potentials and so on. And how they scale here, I don't know. But it's a good question. Yeah. Okay, so let me just summarize as a little take-home before the break. Yeah, so these two approaches are really very complementary viewpoints on the same physics. And then one should distinguish the perturbative regime. So for dark matter energies large in the inflaton mass, and there they agree. So you can use both approaches. Yeah, but in case of doubt, with limited time, this one is probably the better choice, unless you just want to learn the other one, in which case this is an excellent choice. But then there's the non-perturbative regime, where you must use the Bogoliubov approach. Okay, so let's take a break here. And then after the break, I guess we can continue. So this is the final dark matter candidate that I want to discuss. It doesn't mean that there are no others, but well, I told you in the beginning that there's necessarily some kind of personal selection. But I do think that they roughly correspond to those that are most often discussed. Okay, so in order to understand what primordial black holes are, we need to go a little bit through sort of basics of density perturbations and how to describe them, because this is something that is not covered like in any introductory course on cosmology. Cosmology probably yes, but not GR. Yeah, so basically what we want to do in the Friedmann-Robertson-Walker line element, the energy density of our perfect fluid is just depends on time, right? So we have homogeneity. So now we want to replace this with a background density, so the dominant homogeneous component that is time dependent, but then add some perturbations that depend both on time and space. And then isotropy still tells us that the spatial dependence here is that, I mean, once I do a Fourier transform, it's just a function of the total, of the absolute value of the momentum. And then also the standard assumption backed by observations is that these are uncorrelated. So what does that mean in Fourier space? Well, if I look at the correlator between density fluctuations with different momenta, so different scales, then these are just proportional to the delta function. So there's no correlation, in other words, between different scales. And this is also the way to introduce what is known as the power spectrum of density fluctuations. And then there are several different conventions, and that's one of the reasons what I want to introduce it here. Yeah, so it's basically the power spectrum is the proportionality factor here. Yeah, and then for reasons that become clear, one very commonly used assumption or convention is to extract a cubic scaling of the momentum here, of the wave vector, wave number. Okay, so then physically, what we are also often interested in is, I mean, this is in Fourier space, so this is often a slightly complicated sort of, it's slightly complicated to get an immediate intuitive visual impression of what this means. Yeah, so what we somehow have in mind is that, well, a scale k in Fourier space roughly corresponds to the inverse scale in position space. Yeah, but then we can actually formulate this a bit more exactly. Yeah, so if we have some spatial region R and a background that is given by the background density, and here in the spatial region we have an overdensity that is on average given by this delta R. Yeah, then we can directly relate this to the power spectrum. So it's the average density fluctuation at scale R. Yeah, so in principle, this depends, of course, on the position, though if we have a homogeneous space, it doesn't on average. So how do we get this? Well, we basically have to do a volume average over this region, right? And so we want to do a volume average over this region of the density contrast inside the region. Yeah, but then, I mean, we somehow, I mean, of course, physically you would say that, okay, I just integrate exactly over this volume. But then you can generalize this by just introducing some arbitrary window function. Yeah, so the window function is just any function. It's just a function of one parameter that is like essentially 1 for the argument being smaller than 1, and essentially 0 for the argument being larger than 1. But then how exactly the transition looks like, you can choose. Yeah, so for example, if you use a top hat, yeah, then it's just like this. Yeah, so that means it's really physically the average density in that region you would consider. But then it can be useful to use a sort of smooth version. You can also use some kind of Gaussian distribution here. Yeah, so it depends on your problem. So it's partially driven by the physics that you want to describe, and partially driven by how well you can sort of analytically treat the resulting expressions. Yeah, it's just to keep in mind that sometimes people use this without specifying what's actually behind it. So that's why I wanted to stress this here. Okay, so then we can calculate the variance of these density fluctuations. So my variance, variance at the scale R is the variance of this object. Now this is, well, just a statistical thing, right? So you need to square this, you need to use this definition of the correlations such that you can express this in terms of the power spectrum. So what we find then, that's an integral over the window function, or the Fourier transform of the window function. So this is the k here, and the power spectrum. And now you see why this specific normalization of the power spectrum is useful, because this expression takes a simple form. Otherwise, you would get other kind of numerical prefactors involving pi's and so on. So, for example, let's continue here. So let's say that the power spectrum, the power spectrum is just a power law. Yeah, so let's parameterize it like this. Then we can, remember that this kind of expression, the way it is stated, depends both on the scale, on the momentum k, and on time. But we can get rid of the time dependence by specifying at which time we want to evaluate it. And the standard way to do so is to, or one possible and intuitive way is to say that, okay, we want to evaluate it at the time where the scale k enters the horizon. So note that, it's both intuitive and not intuitive, because it means that for every k, we evaluate it at a different time t. So it's not at a fixed time, but at the corresponding time at horizon entry. So at horizon entry, so that means that R is the horizon scale. Then we get this quantity sigma h. That's how it's typically introduced, which is just this one evaluated at the time of horizon entry of this guy k, and that scales like k to the n minus 1. So again, with these definitions that we have, and you have this scaling of the power law, it means that at the time the microphone just died. No, now it's there again. Okay, so what have we learned so far from direct observations? So the smallest scales that we can test the largest scales that we can test are basically the scales given by the CMB. But then there are also other scales that we can test explicitly at smaller scales. So baryon acoustic oscillations, structure formation, galaxy counts, these kind of things. And what we learned from that is that this sigma h here is of the order of 10 to the minus 4. Again, that's one of the reasons I introduced these definitions and normalizations, because the standard jargon is to say that the typical density fluctuations are of order 10 to the minus 5. But using these definitions, it's 10 to the minus 4. So often you see this object here, delta H, and that's the thing that is, it's roughly 5 times this. Sorry, this is roughly 5 times this, and this one is of the order of 10 to the minus 5. So just to avoid confusion here. And we also learned that we have a spectral index that is roughly 1, but actually smaller than 1. So we have a scale invariant spectrum, not quite, actually a red tilted spectrum, meaning that we expect on very small scales smaller power than this one, generically. And we also know, just from observations, that we have to a very good accuracy a Gaussian spectrum. So what does that mean? The probability to find at any given scale R, so I draw an arbitrary circle on the sky or a sphere, and then I ask what's the probability to find a given density perturbation delta R inside the sphere. That's Gaussian distributed. So of course this is just, what I'm saying is that all observations are consistent with this simple picture. Of course you can play around and look for non-Gaussianities, and there's a big industry there. But this is at least what we actually observe. Okay, so then with this background, let's look at what happens actually during gravitational collapse. So basically, we want to again look at this kind of situation here and ask, okay, what will happen? So let's say that we, strictly speaking, have a large patch of the universe that is just homogeneous. and like this smaller patch here, approximately spherically symmetric, that has an overdensity. Yeah, so then you would say that, okay, at some point probably, I mean, both will expand with the Hubble flow, but the Hubble flow is different in this patch and this patch. Yeah, and at some point this will stop and contract. Yeah, and then the question is, okay, will it actually completely contract? So collapse or not? So that's the thing that we want to study. So, and then just to have some estimates, we can look at the energy to overcome the pressure. Yeah, so if it actually collapses, yeah, the energy or the force that acts outwards is the pressure. Yeah, so the pressure, well, from the pressure, we get the force by multiplying with the area of the sphere. So I don't take into account fact. Okay, yeah, works again. Great. Okay, so that means we collapse if the region is larger than, well, we just solve for R here. So we get the Planck mass and the square of the density, inverse density. And I mean, this is something that you have seen before. This is the Jeans length, as expected. Yeah, and of course, you really need the this here, the pressure. Yeah, so if you send the pressure to 0, clearly you collapse in any case. Yeah, there's nothing that could stop the collapse. But if there is some pressure, like during radiation domination in the early universe, you basically need sufficient mass to overcome the pressure and to guarantee gravitational collapse. Okay, so if we want to describe this thing in a bit more of a GR language, yeah, so more proper GR treatment, yeah, then we can basically directly relate to this kind of situation. Yeah, so we have some region outside, and there we assume a flat universe, so no overdensity, and that means that the line element here is just given by the flat Friedmann-Robertson-Walker solution. While here we have some overdensity, and the line element is the one that is given by a Friedmann-Robertson-Walker solution of a closed universe, yeah, with a positive curvature. Yeah, and of course, I mean, as long as these scales are completely separate, you basically solve the line element in this region here, and you solve the line element in this region. They are independent. And then you just have to make sure that you apply correct matching conditions. And that means that you can, starting from some initial time, you can describe the evolution inside this region here as a function of the coordinates of that region. Yeah, so that's also what you do later in the universe when you have ordinary density fluctuations during matter dominations. So if you have seen this, you find, for example, that, I mean, as I said in words before, that this region and that region, they just expand just with different rates. Yeah, so as you would expect, this is an overdense region, so it expands slower. Then there's a turnaround, yeah, and the turnaround is defined by this region not expanding anymore. And you can calculate the overdensity here at the point where this happens. And this is this density contrast of 1.68 something that you might have seen. So there's an analytic solution to this. Yeah, so just for those who have seen this. So let me just write down this. So we have two independent Friedmann-Robertson-Walker patches. And then we need to, well, be careful with identifying the boundary conditions and coordinate choices. and then we identify the time at which the collapse starts, or the turnaround time. That's what I call with denote with a TC, at the point where the Hubble expansion stops in this overdense region. Yeah, and since I solve this and express this after I specify my boundary, my matching conditions, I can express this as a function of the external time or the external coordinates. Yeah, so that means that I actually get a function that depends on the overdensity. And importantly, as a function of the initial overdensity. So not only as the overdensity during at the point of turnaround. Yes? There was a question? Yes. Okay, maybe later. Okay, let me know. Yeah. So again, of course, like the density, of course, grows here while the universe expands. So turnaround happens at a point when the density is larger than the initial density, but the matching conditions allow me to express the time of turnaround as a function of the initial overdensity. Yeah, so that's the point of this exercise. Okay, but then I can use, essentially, at the time of turnaround, I can use this kind of criterion to determine whether eventually I will have a complete collapse, like nothing stops me to actually form a black hole, or whether something complicated will happen as during ordinary structure formation. Yeah, so in ordinary structure formation, during matter domination, it's exactly this kind of story. Yeah, but of course, in the end, it's not a total collapse. Yeah, there's some violent virialization, and galaxies form, and these kind of things. But if we have actually, during matter domination, this cannot happen. During radiation domination, this cannot happen, so we will have a collapse. So that translates then to a condition that this initial overdensity should be larger than roughly the equation of state. Yeah, so, and I evaluate this. I mean, you can state this after you have identified this solution at any time. Yeah, but I evaluate it at the time of horizon crossing of this scale. Yeah, so that means that, well, here we had basically, this is roughly by the Friedmann equation, the Hubble scale at turnaround. So at time tc. But now we have re-expressed everything at the time at which the scale enters the horizon. Yeah, so you always have to, when you do this kind of scale comparisons, and when you express, I mean, also these kind of objects, you have to be careful with specifying at which time, because the density contrasts, they evolve with time. Yeah, so that's what you have to be really careful with. Okay. Okay, so what does that mean? It means that I have collapse. This region will collapse to a black hole if this condition is satisfied. And the time of collapse is actually rather soon after horizon crossing of the corresponding scale. So I form a black hole, primordial black hole, which is given roughly just by the mass inside the horizon. So strictly the scale of this region at the time of turnaround, but this is roughly the horizon mass. So just this one. So numerically, how does that look like? Well, it's something like 10 to the 15 grams for a formation time of 10 to the minus 23 seconds. Yeah, so these things form very early in the early universe. And well, the surprising thing is the mass scale here. Yeah, so remember, the sun weighs about 10 to the 33 grams. Yeah, so these are super small black holes. So these things can be arbitrarily small. Yeah, so as long as you don't go to Planck mass sizes, when we don't know that our description of gravity works. And this is, of course, a big difference to astrophysical black holes. Yeah? So you know that in order to form a black hole, you need, from stellar collapse, you need the star to have like 2 to 3 solar masses at least. Yeah? Otherwise, you don't collapse to a black hole, but maybe form a neutron star or something that is less dense. And then, of course, the point is that this kind of objects, the question is whether they could actually be a non-baryonic form of dark matter. Yeah, so non-baryonic sounds strange at first because we have ordinary matter collapsing, but the point is that the formation happens much, much before BBN. Yeah, BBN is at about a second. So at the time of BBN, these are just completely secluded mass densities. Yeah, so they really appear like a non-baryonic cold dark matter component. Yeah, so there's no, typically baryonic dark matter explanations are excluded by BBN. They would change Big Bang nucleosynthesis. Yeah, so this is indeed correct that this would be a non-baryonic dark matter contribution. Okay, numerically, so this was just a semi-analytic argument. You can do the same thing numerically. You can study the formation of black holes, and then you find that the collapse of these objects is actually something that you can describe with the language of critical phenomena. Yeah, that means that you basically have a something like a phase transition at a critical overdensity. Yeah, so the black hole mass is not always given by the horizon mass, only if you're significantly above some threshold, and has this kind of scaling. Okay, I used an eta here, so it's not conformal time, just a parameter. So during, radiation domination, just to give some context, this critical overdensity that you need to form a black hole at all is about 0.4, and the scaling parameter is about 0.35. And of course, you can determine these things also during other equation of states dominated epochs. So for example, if there's an early matter domination era, then these numbers would be different. This is for standard cosmology. Okay, so then let's look at the abundance of these objects. Okay, so what we want then is the probability to form a primordial black hole of a given mass of the order of the horizon scale. So let's take this kind of situation, not too close to the critical overdensity. And as we've seen, that this is basically the probability to collapse a region of size r to a black hole. Collapse a region of size r at the scale of the Hubble horizon. Okay, So this probability we define as beta. And well, if we use our knowledge of the perturbation spectrum that I told you about, so in particular, if we have Gaussian density perturbations, then what we should do is basically to to integrate. I mean, I had this simple condition before, yeah. So basically, to integrate the entire probability distribution of overdensities over this condition. So black holes will form if I have an overdensity larger than this critical threshold, and they will not form if I'm below this. So then let's use this. So, and that's why I introduced all this notation before. So the only condition is that we integrate from some lower bound. And well, I mean, what we have here is basically an incomplete error function. So it's because you have this exponential dependence only determined by the lower bound. So to a very good approximation, we get this one. To sigma h squared of tk. Okay, so then I told you before what we know about the power spectrum. So if we just use sort of what we know, just based on expectations, we know that, well, this one I told you is like 0.3, 0.4 or so. This one is order 10 to the minus 4. So the expectation is something like this. So this is a factor of 10 to the minus 4. Well, and this one is a factor of 10 to the minus 7 or so, but in the exponent. So this is basically very, very small. So it's really consistent with 0. So you don't, I mean, if there is, I mean, anything that we learn from observations of the power spectrum, the conclusion is that, interesting, things could collapse to a black hole, but the number that we, or the probability for this to happen is 0. Even like playing the lottery is a much, 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 much higher chance to win, jackpot, than to find a single black hole, primordial black hole. Okay, so then you say that, or people say that, oh, well, I mean, I'm sort of exaggerating a bit, because of course, these things, yes? No, exactly. I just wanted to comment on this. So this is the probability for a region in the early universe to collapse. So this is a conditional probability in the very early universe. And that's exactly what I want to say now, because then sometimes the argument is, oh, it's actually not that bad, because, well, once we form them at extremely early times, now I've wiped it out, like 10 to the minus 23 seconds for these light black holes, they immediately start to redshift like cold dark matter. Just like an equation of state of 0. So the redshift is of the energy density is h to the minus 3 rather than h to the minus 4. So they will soon start to dominate the energy budget. But okay, so how do we get then the contribution to the energy density today? Well, we can actually take that into account in a very simple way, because the relative redshifting to the matter density, to the background radiation density, is just one factor of the scale factor of the redshift. Yeah, so the higher the redshift at production, the more we will have today. But this stops at matter radiation equality. Yeah, so we can take that into account by just multiplying this with the amount that radiation contributes today to the universe. Yeah? So this factor here, basically, I mean, the idea is that you have a full 1 plus z, so redshift scaling during radiation domination, but then it's constant. Okay, so again, we can evaluate this numerically. And what we find is that this is some beta to the 10 to the minus 8. And now this time expressed in horizon masses, or then black hole masses, like this. Yeah? So that means in order to produce primordial black holes of order the horizon mass, we need an initial probability to form then of 10 to the minus 8. Yeah, and well, there's some scaling that depends somewhat on the mass, but this is the number that you should compare to this number. Yeah, so we don't win anything by this argument. Yeah. So that means the only way to actually produce them is to strongly modify this one here, yeah, or this one. So we need to strongly modify the power spectrum at small scales. Yeah, just invent something postulating that the power spectrum looks completely different from what we actually observe. So, and that's why I really insist on the fact that this is actually sort of a beyond standard model way around. Yeah, so you have to add new physics to get a non-standard power spectrum. Yeah, so then things that have been discussed are, for example, that you could have a blue tilted spectrum. Yeah, so again, the observation at the scales that are accessible are indicate a red tilted spectrum. Yeah, so then you could imagine that, I mean, if you plot the power spectrum, so it's roughly scale invariant, actually slightly red tilted, then at smaller scales, it goes up again. Yeah, that's the kind of picture that you would have. But then generically, we are in trouble again, yeah, because if it for some weird reason turns up again, you see what happens here. Yeah, then we exponentially overproduce these objects. Yeah, so in other words, in order for this to work, you have to somehow make sure that you cut it here at some point. Yeah, if you cut it like an epsilon higher up, yeah, you will overproduce primordial black holes by 100 orders of magnitude. If you cut it an epsilon below, you will underproduce them compared to dark matter. Yeah, so it's really, I mean, it's not an easy game to play. Similar comment about small-scale peaks in the power spectrum. Yeah, same story. Now I wiped it out, but you can you can invent indeed inflationary models that peak sort of at a given scale. Yeah, and then you can adjust things such that you get well, the correct abundance. Yeah, but the price to pay is that you need a very, very exotic inflationary model. Yeah, so for example, things that have been discussed are if you have some kind of inflection point, so a potential like that, you can have potentials that for some reason have a jump in the first derivative. Yeah, so something like this, where the derivative is not continuous. Yeah, that induces at this scale additional power. Yeah, but if you ask me, okay, what kind of realistic model produces this kind of things, then it's hard. Yeah, you have to by hand write down a potential that does this. And of course, it's an invertible problem, right? I mean, if you want to get a specific power spectrum, yeah, you can always write down the corresponding inflationary potential, but that doesn't tell you that this is a realistic one. Yeah? So typically you need like multi-field inflations, and that's why, again, this is a BSM story. Yeah? So it's not, I mean, I just want to bring home the message that, okay, these are very interesting candidates, yeah, but don't call them standard model candidates. So that's the main point. And then just to complete this list here, what's also been discussed are non-Gaussian power spectra. Again, from what we've seen here, of course, this kind of conclusion here relies on the fact that we have a Gaussian distribution. So if you somehow postulate that at some scale, maybe we have a Gaussian distribution, but then for some weird reason, at exactly delta equal to 0.4, we have a small peak in the distribution. So this is more likely for this. Yeah, sure. Then it will give you the correct number here, but you still need to convince people that this is actually a sensible model. And if you just write down generic non-Gaussianities, that is of course interesting. But there are strong observational constraints. So if you just have a generic modification of the Gaussian spectrum and you parameterize this, and then you place observational constraints on that, that's not the kind of non-Gaussianity which gets you around this one. Okay, we still have a little bit of time, I think. So maybe I just want to conclude by mentioning briefly that there are also observational constraints. So the point is that, primordial black holes are interesting, but here this is a lecture about dark matter. So the question is not whether they exist or not, but whether they could make up the dark matter, and whether they could explain all of the dark matter. So we're interested in this ratio here, where that is the primordial black hole density divided by the observed dark matter density. And then this ratio being 1 is excluded for a large range of masses. So that's completely independent of these considerations about how to produce them. So in particular, the low mass range, so smaller than about 10 to the 16 grams or 10 to the minus 17 solar masses, we have constraints from Hawking radiation. So these very small black holes are so small that they actually radiate energy in a sufficient amount or appreciable amount. So just to remind you, the temperature, the Hawking radiation temperature is inversely proportional to the black hole mass. So the smaller the black hole, the more energy is radiated away. And this, of course, also means that, if you continuously radiate away thermal energy by thermal radiation, then at some point you will have radiated away so much that you radiate away the entire black hole. And this happens basically for black hole masses smaller than 10 to the 15 grams or so. So then the lifetime is smaller than the age of the universe. And that gives all kinds of constraints because you have an additional source of energy injection in the early universe. But even today, even if they're still around, they would inject so much energy that you can exclude this. Then we have like some allowed mass range, and then for slightly larger black holes, there are microlensing constraints. And these are, for example, set by direct observations to look for a dark matter candidate that was popular before the WIMP was invented. So maybe you know this historically. The reason why it's called a WIMP is not only because it's a weakly interacting massive particle, but also because it was meant to be an alternative to the dark matter candidate that was discussed before, namely a macho, a massive halo accompanying object. So people thought that you could have just some massive standard model like Jupiter's, like large planets or so, that would make up all the dark matter. And those were looked for in microlensing advance. So you basically search for these objects, these dark objects passing along the line of sight of some distant star, pulsar, whatever, and then the light curve would be modified. And the fact that you don't see these kind of modifications allows you to place constraint. And well, for even larger black hole masses, like starting from solar masses roughly, you have more constraints, gravitational waves, and then not the least accretion. So that constrains CMB, Lyman alpha, and so on. Yeah, so that means there is, in principle here, a gap, yeah, for asteroid-sized black holes, yeah, that could formally constitute all of dark matter, yeah, if you don't care about how likely it is. So this is a currently really open window. I should say that these bounds also come with some caveats attached. So they assume that all the black holes have more or less the same mass. So if you take a very extended black hole distribution and mass, yeah, then there's a little bit of wiggle room to evade some of these constraints. So that's also some industry. But again, it's hard to relate it to a production mechanism that is, well, it's hard to relate it to a minimal production mechanism. Let's put it like this. Okay, that's it. Thanks a lot for joining me so long. I put the lecture notes should be on the internet very soon. So if you have any questions, just get in touch. Also after the school, questions about dark matter, about how to use DocSUSI, whatever. It was fun to be here.